The main turbine is driven by high-pressure steam. The spinning turbine is connected to the generator, where the motion is used to generate electricity. Very simply put, a generator is a device which moves a magnet near a collection of copper wires to create a flow of free electrons. It may help you to imagine a generator as acting like a pump, pushing water through a pipe. Instead of moving water, the generator uses magnetic fields to push free electrons along a conductor, resulting in the flow of electricity. Conductors are materials whose atoms have electrons that are easily moved. A water pump moves an amount of water molecules and applies pressure to them. Likewise, a generator moves an amount of electrons and applies electrical pressure or voltage to them. If a magnetic field is moved across a conductor, the electrons are pushed at a right angle to the direction of motion, and the direction reverses when the opposite pole passes the same location. This is the final energy conversion at the plant, where mechanical energy from the turbine is converted to electric energy. In commercial AC power, the current reverses or alternates 60 times per second. The on-off effect happens too quickly to see. The main parts of a generator can be described by their physical and their electric roles. The physical parts are the rotor and the stator, or the part that rotates and the part that is stationary. The electrical roles are the field and the armature. The armature is where the field creates the electrical power. In large generators, this is normally on the stator. The field is the part that contains the magnetism. It is shown here being produced by a permanent magnet. This is acceptable for small generators. However, large commercial machines need a field much stronger than a permanent magnet can make. This is overcome by using a heavy rotor with copper windings and creating a spinning electromagnet. A smaller generator attached to the same shaft provides the power for the field. This is called the exciter. The armature windings on a large generator are built with many conductors and outputs 3 conductors or phases that are necessary for running large machines and for transmitting to the grid. The output voltage of this generator is 22,000 volts or 22 kV. The power output from the generator is supplied by the isolated phase bus system to the main transformers. A transformer is used to step up the voltage to match the grid. A transformer contains a core along with primary and secondary windings. When there are more windings on the output or secondary, then the transformer is a step-up transformer. This transformer's ratio, or primary and secondary windings, is 1 primary for 10 secondary. The main transformers perform the same function, but due to the size of the coils and power, they are filled with oil and use forced cooling from fans. This means the 22 kV input from the generator is stepped up to 220 kV for transmission. High voltage is used to transmit power over long distances. There are fewer losses because the power is transmitted at lower current. In the United States, voltages as high as 500 kV are used, and worldwide there are now 1000 kV or 1 million volt transmission systems.